So moving on, the molecular interpretation of equilibrium constants. So what this is related to, the only thing I'm going to say about this is how equilibrium constants can be related to the thermodynamic potentials. Okay, so we know now that K equals the exponential of negative, the standard free energy of the reaction divided by RT. Okay, we can write that the standard free energy of reaction is equal to the following: delta H of reaction minus T delta S of reaction. And so I can substitute that into K. And this would have been an exercise that we would have played with more in Igor with some data fitting. But you guys are probably sick of data fitting, so we're going to move on. Okay? So now I can rewrite this expression putting in this, plugging this into delta G, and I get the following: exponential of the negative delta H divided by RT times the exponential of, and this is going to be delta S of reaction, just divided by R, because I have that T times delta S. All right? And so now what we can get out of this actually, through graphical analysis, if I take the natural log of both sides, then I get the natural log of K is equal to the negative delta H of reaction divided by RT. Let's see, and then that's plus delta S, oops, I said G, I said S, but I wrote G, plus delta S of reaction divided by R. And of course, if I were to do a graph of the natural log of K versus 1 over T, this would actually help me establish if a reaction is endothermic or exothermic, okay? Because if a reaction is endothermic, I have a negative sign right there, so I would see a negative slope from this. Okay, so this is for delta H greater than 0. So that would help me establish, like, molecularly what's happening with the reaction. Is it endothermic or exothermic? And if I see that a reaction is exothermic, I will actually get a positive slope out of this thing. Delta H is negative because negative negative makes a positive, right? Okay. Fantastic. And so what this means is when you have, so in terms of equilibrium, what this favors now, okay? So if I go back to this expression right here, talking about this expression, we also remember from our Gen Chem, what does K greater than 1 mean and what does K less than 1 mean? Hopefully this is, you remember this, but K greater than 1, we know favors products, and K less than 1 favors reactants. So what can we say about the delta H and the delta S in light of these two conditions? Okay. Well, if we have a delta H greater than 0, what does all of that give us? Well, a delta H greater than 0 means that this exponential is going to be negative, and the exponential of a negative quantity is less than 1. So a delta H that's greater than 0 has a tendency to favor reactants. Okay? Similarly, if the delta H is less than 0, so we have a negative times a negative, which gives me a positive, and the exponential of a positive number gives me a number that's greater than 1. So with exothermic reactions, there's a tendency to favor products. Now, of course, we have to consider what's going on with delta S, right? And so what we should establish for all delta S of reaction greater than 0, so in other words, for all spontaneous reactions, okay, will favor products. right? Because if a reaction is spontaneous, its delta S is greater than 0. That's the exponential of a positive term. The exponential of a positive term gives me something greater than 1. And when K is greater than 1, it favors products, okay? And so now what's a really interesting case here is when you have an endothermic reaction that's spontaneous. It can happen, okay? And that really, we have to now look at what's going on with the temperature. So think about this now. Let's back this up here. So I'm just going to try to describe this conceptually, okay? If we have a spontaneous reaction, we know that that's favoring products. But what if that reaction is endothermic? That's going to favor reactants. So what this means now is there's a competition between these two chunks. One chunk will be greater than 1, the other chunk will be less than 1, and when we multiply them together, that's going to tell us what won. Did the entropy win or did the enthalpy win? And as it turns out, the temperature of that situation is critically important. So in other words, if the temperature is sufficiently large, I think I ran out of slides here, but let's add another slide. If T is sufficiently, assuming I can spell, and let's go back to this expression, right? K equals the exponential of negative delta H over RT times the exponential of delta S over R, okay? If T is sufficiently large, then if you think about it, what that means is this term will be small. So even though it might be endothermic, which might favor reactants, if T is sufficiently large, there's enough thermal energy to still drive that reaction spontaneously on to products, okay? So what's also cool about this, what this also establishes, so now we'll say if T is sufficiently large, endothermic reactions can favor products. So what about the other case? What about an exothermic reaction? Well then, if T is sufficiently, I can't spell, whatever that says. If T is sufficiently small, then an exothermic reaction will also favor products. So this is actually why exothermic reactions are more efficient when it is colder. And the reason for that is because now you have a negative in this term, so that gives you a positive. But when T is small, it's going to make this number really big. And the exponential of a really big number is an even bigger number, which gives you a humongous K favoring products, okay? And so now I'm looking at the time. I've been talking for 40 minutes now. And so what this